In this lesson, we want to review solving quadratic inequalities. So a quadratic inequality is of the form, we have ax squared plus bx plus c is less than 0, where we can say that a, the coefficient of x squared, b, the coefficient of x to the first power, and c, the constant term, represent any real number with one exception. We can't have a allowed to be equal to 0. Because if a is 0, our x squared term would disappear and we'd no longer have a quadratic inequality. Now, additionally, in this definition, we can say that our less than here could be a less than or equal to, a greater than or equal to. All right, so how can we solve a quadratic inequality? Well, there's quite a few different methods that you can use. We'll talk about a method that relies on graphing kind of later on in the course. Graphing is good to conceptualize what's going on, but it's not necessarily the quickest method. In most cases, it's not going to be quickest. So we're going to focus on a method that relies on test values. So for solving quadratic inequalities, the first thing we want to do is we want to write the inequality as an equation and solve. So what this is going to do is it's going to give us our boundaries, okay? Or some people will call them endpoints. Some people will call them critical values. Now we're going to use the solutions from the equation to set up intervals on the number line. And again, we'll see that in a moment when we look at an example. Then this is the important part here. We're going to substitute a test value from each interval to determine the solution set. Now, the problems we're going to look at today are going to be inequalities such that when we transform them into equations, these quadratic equations are going to have real number solutions, and more specifically, they're going to have rational number solutions. So these are going to be kind of easier examples just to get the concepts down. You can work with these when the equations have complex solutions and also when they have irrational solutions. But we'll talk about that later on, again, when we revisit this topic using graphing. All right, so let's go ahead and take a look at the first example. So we have x squared minus 6x is greater than 16. So the first thing I'm going to do is kind of write this where my quadratic expression is on the left side and 0 is on the other side, okay? So I can do that by just subtracting 16 away from each side of the inequality. I'll just write this over here. This would cancel and become 0. I would have that x squared minus 6x minus 16 is greater than 0. Okay, so now what I want to do is I want to change this inequality into inequality. So all I got to do is change this greater than symbol to an equal symbol. So I'm going to make this into x squared minus 6x minus 16 is equal to 0. So I can solve this using factoring. I can solve this with my quadratic formula. Whatever you want to do, it's pretty easy to solve this with factoring. So let's just do that. So this would be an x, and this would be an x. So give me two integers whose sum is negative 6 and whose product is negative 16. We know that would be negative 8 and positive 2. So now I can just set each factor equal to 0 and solve. So I would have x minus 8 is equal to 0, or I would have that x plus 2 is equal to 0. For this one, I can add 8 to each side of the equation, and I'll get that x is equal to 8. For this one, I can subtract 2 away from each side of the equation. I'll get that x is equal to negative 2. So let's erase all of this. We don't need any of it anymore. We just need these solutions. So at x equals 8 or at x equals negative 2, we're basically saying the left side of this quadratic inequality is going to be 0. So here's 8 and here's negative 2. So what I'm going to do is I'm going to put a vertical line at each to kind of separate the number line into intervals. So anything less than negative 2 or anything to the left of negative 2, let's just call this interval A for reference sake. Anything between negative 2 and positive 8, let's call this interval B for reference sake. And anything that's greater than 8, or you could say anything to the right of 8, let's call that interval C, again for reference sake. So 3 intervals on the number line. What we're going to do is test a value in each interval and see if it works in our inequality. And the reason this works is that, again, at 8 or negative 2, the left side here is going to be 0. Now, all other numbers other than 8 or negative 2 will make the left side either negative or positive. And the sign of the quadratic expression can only change from positive to negative or negative to positive at a number that makes it 0. So this means that if a number in the interval that we test, so if a number in interval A, or a number in interval B, or a number on interval C, if a number in one of those intervals satisfies the inequality, then every number in that interval will satisfy the inequality. The reverse is true. If a number in that interval does not satisfy the inequality, then no number in that interval will satisfy the inequality. So in interval A, let's just go ahead and choose something like -4. That would be a good test point. And we can try that in this guy right here. So let's plug in a -4 everywhere we see an x. And so we would have -4 squared, which is positive 16. Then -6 times -4 is plus 24. Then you'd have minus 16, and this is greater than 0. Well, we know that 16 minus 16 is 0, so you have that 24 is greater than 0, which is true. So I'm just going to put for interval A that this is true. Okay, so every number in interval A would work. Now, let's choose something in interval B. Using 0 is always pretty quick, so let's choose that. Let's plug in a 0 for each x. You would have that -16 is greater than 0, which is false. So for interval B, we'll say this is false. And then for interval C, let's choose a value of 10, because that would be pretty easy to work with. So 10 squared is 100, minus 6 times 10, which is going to be 60. Then minus 16 is greater than 0. 100 minus 60 is 40. 40 minus 16 is 24. 24 is greater than 0. This is true. So for interval C, we'll say it's true. Okay? So let's erase all of this. We don't need this anymore. And you can label this visibly. You can say that interval A is true, interval B is false, and interval C is true. In most of the situations you're going to look at, when your quadratic inequality sets up as a quadratic equation with real number solutions, you're going to basically have 3 intervals where either the left interval and the right interval are going to work and the middle doesn't, or where the middle works and the 2 on the outside, so the leftmost interval and the rightmost interval, don't work. Okay? So in this situation, we have that anything to the left of -2 would work. So x is less than -2. Or we have that anything to the right of 8 would work. So x is greater than 8. Now in this particular case, because we have a strict inequality, we see that our endpoints don't work, right? If I plug in a -2 or an 8, again, the left side would be 0. 0 is not greater than 0. So -2 is not a solution, and 8 is not a solution. So let me erase this and kind of drag this over here. We can write our solution also in interval notation. We could say that from -infinity up to but not including -2, and the union with, we have anything larger than 8. Okay? So this is our interval notation. This is using x. We can also kind of graph this on a number line. So we could say, again, anything less than -2. I'll put a parenthesis at -2 to show it's not included. I'll just shade everything to the left. We also said anything greater than 8. I'll put a parenthesis at 8, shade everything to the right. All right, so that one was pretty easy. This one's also going to be easy, but just a little bit more tedious. So we have 25x squared plus 71x plus 16 is less than or equal to -7x squared minus x. So again, the first thing I'm going to do is write this as a quadratic expression on the left, 0 on the right. So I can add 7x squared to both sides of the inequality. And I can add x to both sides of the inequality. So this is going to cancel and become 0. Now 25 plus 7 is 32. So this will be 32x squared. And then plus 71 plus 1 is 72, so 72x. And then plus 16 is less than or equal to 0. Let's erase this, and we'll just kind of slide this up. Okay, so let's replace the inequality symbol with equals and solve that equation. So we're going to have 32x squared plus 72x plus 16 is equal to 0. Now each number in this equation, the 32, the 72, and the 16, are each divisible by 8. So 32 divided by 8 is 4, so this would be 4x squared. 72 divided by 8 is 9, so plus 9x. 16 divided by 8 is 2, so plus 2, and this equals 0, right? Obviously 0 divided by 8 is still 0. So let's erase this. Anytime you can make the equation simpler and work with smaller values, it's always a little bit better. So for this guy, I could solve it using factoring, or I can use my quadratic formula. Because this number right here is not prime, it's probably going to be faster to use my quadratic formula. So the 4 here represents A, the 9 here represents B, and the 2 here represents C. So my quadratic formula, in case you forgot, is x equals the negative of b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so negative b, we have negative 9 plus or minus b squared. 9 squared would be 81 minus 4 times a times c. Well, a here is 4, c here is 2. So negative 4 times 4 is negative 16. Negative 16 times 2 is negative 32. So this would be minus 32 here. Then we have 2 times a in the denominator. A is 4, so 2 times 4 is going to be 8. So then under our square root, we have 81 minus 32, which is 49. And the square root of 49 is 7. So we have negative 9 plus 7, which is going to be what? It's going to be negative 2 and then over 8. So we'll say that one solution is x equals negative 2 over 8, which we know would simplify to negative 1 over 4, so negative 1/4. Then the other solution would be negative 9 minus 7, and that's going to be negative 16, and then negative 16 over 8 would be negative 2. All right, so let's erase all this. We don't need this anymore. So we can see our two kind of critical values or boundaries are negative 1/4 and negative 2. So at negative 2, I could draw a kind of vertical line there. And then negative 1/4, we don't have a notch for it, but let's say it's about right there. So I'm just going to label this as negative 1/4. And let's just put a kind of vertical line there as well. So I'm splitting this up into 3 intervals. Anything to the left of negative 2 is interval A. Anything between negative 2 and negative 1/4 is interval B. And anything to the right of negative 1/4 is interval C. All right, so let's just pick a test value for each of these. And let me write my 0 there again. So let me divide this by 8. So this would have been 4x squared, and this would have been 9x, and this would have been 2. Again, just doing that so I have smaller values to work with. So I'm going to pick in interval A a value of negative 4. So let's plug that in there and also there. So negative 4 squared is 16. 4 times 16 is 64. And then 9 times negative 4 is going to be negative 36, so minus 36. And then plus 2. We don't even need to do the kind of operations here. We know that this would not be less than or equal to 0. So anything in interval A would be false. Okay, this would be false. So let's erase this. And now let's look at something in interval B. So again, the way most of these work, if something in interval A doesn't work, then B will work and C won't work. Okay? So for B, let's pick negative 1. So let's plug that in here and here. So negative 1 squared is 1. 1 times 4 is 4. So 9 times negative 1 is minus 9. And then we have plus 2, and this is less than or equal to 0. We can tell that this is going to be negative on the left, right? So it will be less than 0. So we can say for interval B, it's true. And then again, in most cases, okay, not every case, but in most cases, if A works, the leftmost region, then B will not work, and C, the rightmost region, will work. So you have a case where kind of the leftmost region works, the middle region doesn't, and the rightmost region will work. The other case that happens a lot will be that the middle region works, and the one on the left and the one on the right don't work. Now, this isn't true every single time, but in most cases it follows this pattern, okay? So for region C, let's pick a value of 0, because that's going to be available. It's real easy to work with. So I'm going to plug in a 0 there and there. So we know this would be gone and this would be gone. You would have that 2 is less than or equal to 0, which is false, okay? So let's erase this. We have our solution region now. Interval B does work. Anything between negative 2 and negative 1/4. So x is greater than or equal to, because we have a non-strict inequality, negative 2, and less than or equal to, again, because we have a non-strict inequality, negative 1/4. Whenever you have that non-strict inequality, the endpoints are going to be solutions, okay? So we can show this in interval notation. Put a bracket here. We'll have negative 2 because that's included, comma, you'll have your negative 1/4, and then another bracket. So graphically, let me kind of keep that notch there for negative 1/4. Let's put that right there. What we're going to do is we're going to put a bracket at negative 2 and a bracket at negative 1/4. Just shade everything in between. So this is our graphical solution. This is interval notation. And then again, we can write this with our variable x and just say that x is greater than or equal to negative 2 and it's less than or equal to negative 1/4. All right, let's take a look at another one. So we have negative 2x squared minus x plus 3 is greater than 0. So in this case, I have my quadratic expression on the left and a 0 on the right. So I can just change this greater than here to equals and solve the resulting equation. So we have negative 2x squared minus x plus 3 is equal to 0. I can solve this using factoring pretty quickly. So I know that I can first divide everything by negative 1 so that the leading coefficient is going to be positive. That just makes it easier for me to factor. So I'm going to say this is positive 2x squared, and then we're going to have plus x minus 3 is equal to 0. Okay, so let's just erase this. And I can factor this on the left side here pretty quickly because this 2 is a prime number. So this would be 2x and this would be x. I just got to work out the outer and the inner such that I get a plus 1x as my middle term, right? So the last term here is a negative 3. That can only come from a positive 1 times a negative 3 or a negative 1 times a positive 3. So if I want a positive 1x as the middle term, I would want to put a plus 3 here and a minus 1 here, right? Because the outer would be negative 2x and the inner would be plus 3x. If you sum those, you get plus 1x, okay? So I'm now going to set each factor equal to 0. So 2x plus 3 equals 0. Then or, I'm going to set x minus 1 equal to 0. So for this guy, I'm just going to subtract 3 away from each side of the equation. I'll get that 2x is equal to negative 3. Divide both sides by 2, and I'll get that x is equal to negative 3/2. For this guy, I would add 1 to each side of the equation, and I would get that x equals positive 1. Okay, so I'm going to erase all this. I don't need any of this information anymore. I'm just going to kind of drag this up here. These are our critical values, or again, the boundaries of the endpoints. It's basically going to be the values that make this left side 0. Okay, so negative 3/2, we can just say that's, again, halfway between negative 1 and negative 2. In decimal form, it's negative 1.5. So let's just say that's right there. So this is negative 3/2. And then we have positive 1. So I'm just going to put a vertical line at each just to separate the number line into kind of intervals. So anything to the left of negative 3/2, I'm going to call that interval A. Anything between negative 3/2 and positive 1, I'll call that interval B. And anything larger than positive 1, I'll call that interval C. Okay, so in interval A, let me just choose negative 4. So I'd have negative 2 times negative 4 squared minus negative 4, and then plus 3, is this greater than 0? So minus a negative 4 is plus 4, so we see that. We know that negative 4 squared is going to be 16, and negative 2 times 16 is negative 32. So we can see that this is not going to be greater than 0, so region A, we know that's false. Again, for most of these, not all of them, but for most of these, it sets up to where the one on the left, if that's going to be false, then the middle part is going to be true, and the part on the right is going to be false again. But again, you've got to really test these because you have some special case scenarios. So let's look at 0 for region B. So if I plugged in a 0 for x, this would be gone and this would be gone. I'd have that 3 is greater than 0, which is true. And then for C, let's just choose 4. So if I squared 4, I'd get 16. 16 times negative 2 is negative 32. And then minus 4 plus 3 is greater than 0. We can tell that's going to be false. Okay, let's erase this. So basically, the region that works is region B. And we have a strict inequality, so the endpoints or the boundaries of the critical values will not work. So I can say that x is greater than negative 3/2 and less than positive 1. In interval notation, I would have my negative 3/2 next to a parenthesis, and then comma a 1 next to a parenthesis. Then kind of graphically, let me erase all this. I'm going to keep my notch there for negative 3/2. So graphically, I'm just going to put a parenthesis at negative 3/2 and a parenthesis at positive 1. and then just shade everything in between. So this is my graphical solution, this is my interval notation, and then again, using x is greater than -3/2 and less than 1. So pretty easy overall to solve a quadratic inequality. As we move throughout our course, we'll see some more challenging scenarios, and we'll get to this when we start talking about graphing parabolas, okay? So this would be the graph of a quadratic equation. We'll look at some more challenging situations with quadratic inequalities at that time. So we'll just wrap up our lesson by looking at some special case scenarios, and then as the final problem here, we'll talk about something that's not a quadratic inequality, but that we can use the same thought process to solve, okay? So if we saw something like x squared plus 2ax plus a squared is greater than -k, the idea here is that we know this is generic, but we can show that the left side here is a perfect square trinomial. So this can be factored into x plus a, that quantity squared, right? And this is greater than -k. So don't get kind of tripped up by the fact that this is so generic, right? We have a -k, we have an a. These are kind of foreign things when we see all these letters involved other than x. But again, don't let that kind of rattle you. All we're trying to say here is that in this particular case, I can plug in anything I want for x and I would get a true statement. Well, why is that? This guy over here, this -k, just represents some negative real number. So it could be -3 or -10 or -2 billion, whatever you want it to be. Think about the fact that x can be anything and a can be anything, and I'll always get a true statement. X plus a can be whatever. It could be 0, it could be negative, it could be positive. Once I square this guy, if I square a negative, I get a positive, right? A positive would always be greater than a negative. If I square 0, I get 0. 0 would always be greater than a negative. If I square a positive, I'm going to get a positive, and that's always going to be greater than a negative. So there's nothing you can plug in for x that won't work. So if you see this scenario, you're basically going to have a solution where x is any real number. Okay, so you can say all real numbers. All right, let's look at an example. So we have 9x squared minus 48x plus 64 is greater than -5. So again, if you look at the left side and you have an inkling that this guy's going to be a perfect square trinomial, you check the ends, right? So 9x squared, that comes from 3x being squared. And then 64 comes from 8 being squared. So is the middle minus 2 times this guy, the 3x, times this guy, the 8. Well, 2 times 3 is 6. 6 times 8 is 48. 48 times x is 48x. And you've got the minus there. So this is minus 48x, right? So this is a perfect square trinomial. That means I can factor it into a binomial squared, right? This would be 3x minus, right, because you have the minus there, the 8, that quantity squared. Let me make that a little better. And this is greater than -5. Well, as we just said, this is going to be true for all real numbers, right? It doesn't matter what I plug in for x here. I'm going to multiply it by 3. I'm going to subtract away 8, no matter what it is. If it's negative, or if it's 0, or if it's positive, when I square it, it's either going to be 0 or some positive number. So it's always going to be greater than -5. So this is true for all real numbers. So for this, I can just write all real numbers. Now, another thing I can do, you can kind of erase this, you don't need this anymore. You can write this in interval notation from -infinity to +infinity. You might want to do that. Or lastly, you can just shade the entire number line, right? So shade this arrow and then all the way through, and then shade this arrow. Okay, so any real number would work as a solution for x in this scenario. All right, let's talk about the other scenario you're going to come across. So we have x squared plus 2ax plus a squared is less than -k. Again, the left side is a perfect square trinomial, so I can factor this into x plus a, that quantity squared. If I say it's less than the negative of k, so this is a negative number here on the right. So what happens is, if I choose a value for x, it doesn't matter what it is, I add some number a, and then I square that result, I'm always going to get something that's non-negative. So the left side here would be 0 or something positive. And that's never going to be less than a negative value. So when you see this, there's not going to be a solution. Now, if you get something like x squared plus 2ax plus a squared, and that's less than 0, again, this guy right here, this is x plus a quantity squared, is less than 0. This would carry no solution as well. But if we change this and say it's less than or equal to 0, well, what happens is you would have one solution there, okay, in this particular case, because you could set this part right here equal to 0, and you could solve that. That would give you one solution, okay, one value that would satisfy the inequality. The less than part would never work, but the or equal to would work for one value, okay? So let's look at an example. So we have 49x squared minus 140x plus 100 is less than negative 2. So the left side here, I know I can factor this into a binomial squared. This guy here on the left is 7x being squared. This guy here on the right is 10 being squared. And the middle is minus 2 times 7x, which is 14x, times this guy 10, which is 140x. So you have minus 140x. So this would work itself out to be factored into 7x. You have your minus there, so minus the 10 being squared, and this is less than negative 2. This will not have a solution, okay? There's no solution here. So there's no solution, okay? So you can put the symbol for the null or empty set, but again, no value here plugged in for x would give you a true statement. All right, so let's look at one more example here. And so what we have is the quantity x minus 1 times the quantity x plus 2 times the quantity x minus 4 is less than or equal to 0. So this, if I multiplied it together on the left, would not be a quadratic expression. It would be a cubic expression, right? So I wanted to give you one where it's not quadratic, and you can see that you can use pretty much the same process to solve it. So if you multiply this together on the left, you would get x cubed minus 3x squared minus 6x plus 8. Just went ahead and factored that already because we're not at a level where we can factor something like that yet. We'll learn how to do that later on in the course. So if I replace this inequality symbol with equals, I can solve the resulting equation. Because it's already in factored form, this will be pretty quick for us. So we know that our solutions here would be what? You'd have x minus 1 equals 0, so x would be 1. X plus 2 equals 0, so x could be negative 2. And then x minus 4 would be equal to 0, so x could also be 4. So these are our critical values here. So we have that x could be 1. So let's put a visible border there. X could be negative 2. And then x could be positive 4. So we're going to have 4 intervals here. So interval A will be anything to the left of negative 2. Interval B will be anything between negative 2 and positive 1. Interval C will be anything between positive 1 and positive 4. And interval D will be anything larger than positive 4. So let's erase this. I don't need any of this anymore. Let's just choose a point from each interval and see if it works. So for interval A, let's just choose negative 4. So negative 4 minus 1 is negative 5. And then negative 4 plus 2 would be negative 2, so times negative 2. And then negative 4 minus 4 would be negative 8. So is this less than or equal to 0? I don't even need to go through here and multiply. I know that a negative times a negative times a negative, basically 3 negatives, would give me a negative. A negative is always less than 0, so this part is true. So then for interval B, I can use 0, right? That's easy to work with. So 0 minus 1 is negative 1. 0 plus 2 is 2. 0 minus 4 is negative 4. So this guy, because there's 2 negatives being multiplied together, that would be a positive. So for interval B, that would be false, right? A positive is not going to be equal to 0, and a positive is not going to be less than 0. All right, for interval Z, let's choose 2. So 2 minus 1 is 1. And then 2 plus 2 is going to be 4. And then 2 minus 4 is going to be negative 2. So this guy would be negative, so this is going to work. This is true. And then for interval D, we can choose, let's say 5. 5 minus 1 is 4. 5 plus 2 is 7, so it would be times 7. And then 5 minus 4 is going to be 1. So everything here is going to be positive. Again, a positive is not less than 0, and it's not equal to 0. So for interval D, it's going to be false. Okay? So our solution here, again, because we have a non-strict inequality, the endpoints will be included. Anything in interval A, so anything to the left of negative 2 and also including negative 2. So x can be less than or equal to negative 2. Then or anything in interval C, so anything between 1 and 4 with 1 and 4 included. So x can be greater than or equal to 1 and less than or equal to 4. Okay, so those two kind of regions on the number line. So in interval notation, I can say from negative infinity up to and including negative 2. And it's the union with. We'll have anything from 1 to 4 with them both being included. So graphically, we can say that At -2, we'd put a bracket. We'd shade everything to the left. And then at 1, we'd put a bracket. And at 4, we'd put a bracket. Let me make that a little bit better. And then we'd shade everything in between here, okay? So this is our solution graphically. This is our solution using interval notation. And then again, using x, we can say x is less than or equal to -2, or x is greater than or equal to 1, and less than or equal to 4.